Thank you very much for being here on the last day of the school. I appreciate it. So today I'm going to talk about neutrino astrophysics. We've heard a lot about neutrino astrophysics, but today I would like to talk about in a bit of a different light, not so much as a probe of astrophysics, but rather as a probe of particle physics, and more specifically as a probe of the properties of dark matter. So I guess I'll just go with here. Okay. Yeah, it's stuck. Oh, okay. Just a second. This would work. Okay. Yeah. So again, we've heard a lot about neutrino astrophysics, and the original motivation for neutrino astrophysics was, of course, to try to answer a question which was astrophysical in nature, namely, what is the origin of cosmic rays? We know that cosmic rays are these huge energy particles which are difficult to track down because they are charged, and so they are deflected in the magnetic field, which makes it difficult to pinpoint where they come from. And so people started to build detectors for measuring the fluxes of gamma rays and neutrinos, because they expected a concomitant production of gamma rays and neutrinos in the same sources in which cosmic rays are accelerated. And so the final step in this kind of multi-messenger quest for multi-messenger view of the universe has been the detection of high energy neutrinos by IceCube in 2013. And of course, I feel a bit out of place in talking about IceCube on the last day of the school, but I will say a few words anyway. So we know that detecting high energy neutrinos is a very difficult task, mainly because neutrinos are so weakly interacting. And so we need huge volumes of materials in order for them to efficiently interact inside our detector and detect the tracks that come out of the interaction. In IceCube, this is realized by looking for the Cherenkov light that is produced by the charged particles that follow a neutrino nucleus collision. And by this methodology, the IceCube collaboration was able to detect an excess of neutrinos in the region above 60 TeV. So this is, this is energy of the neutrino versus the event rate detected by IceCube, and above 60 TeV, essentially, we weren't expecting any neutrino by atmospheric interaction. And so the neutrinos that were found were essentially identified as neutrinos of astrophysical origin. But what I would like to focus today on here is actually what happens at higher energies, above 10 PeV, which is more or less the maximum energy at which IceCube can detect something. So above the 10 PeV, the methodology that IceCube is using to detect neutrinos is not the most efficient one. What people are actually looking at is actually detection, so-called radio detection. The idea is that when a neutrino collides with a nucleus, it produces, again, a shower of charged particles. The shower as a whole is neutral, obviously, because the neutrino is neutral. But the positive and the negative charges of the shower can separate because they are moving in a medium which is non-charged symmetric. And therefore, it behaves like a moving dipole with the plus and the minus, which are separated. And as we know from classical electrodynamics, a moving dipole produces radiation, which in this case turns out to be in the radio frequency band. So it produces radio waves. And these radio waves can be targeted by arrays of radio antennas. The advantage of radio waves is that they are very mildly attenuated because they have a long wavelength, so they don't really see obstacles. So they can travel long distances without being attenuated. And a number of experiments are under construction to try to detect ultra high energy neutrinos above 10 PeV with this technique. So what I'm showing here is a collection of sensitivities of different experiments as a function of the neutrino energy. Very roughly, we can imagine the sensitivity as being the minimum flux that the experiments will be able to detect. So the ones that will be most relevant for this talk will be essentially RNOG and Grant. Grant 10K and Grant 200K are just scaled up versions of the same experiment that will be built after longer exposure times. And then IceCube Gen 2 is also mounting an array of radio antennas, which hopefully will start taking data in 2030. But okay, so from the experimental point of view, we have no data in this ultra high energy range. We hopefully will have data in some 10 years or 20 years. But from the theoretical point of view, is there a strong motivation for looking into this energy range? Do we expect to see something in this energy range? The answer to this question is yes. There is a strong expectation for ultra high energy neutrinos. There is a guaranteed production of ultra high energy neutrinos, which are the so-called cosmogenic neutrinos. These are expected to be produced by the collision of ultra high energy cosmic rays on the cosmic microwave background. We know that cosmic rays exist. We know that cosmic microwave background exists. So obviously we expect these cosmogenic neutrinos to exist as well. But how many of these cosmogenic neutrinos do we expect to exist? This is a much trickier question because the properties of ultra high energy cosmic rays are not so well defined. So just to give an idea of the uncertainty, here you see this gray band, which is essentially an uncertainty band of different models of cosmogenic production in the literature. You see that this uncertainty band spans practically 2 orders of magnitude. They pass from being practically unobservable here to being observable in less than 10 years here. So clearly, there is a huge uncertainty about how many of these cosmogenic neutrinos exist. And in addition, we also can expect production of ultra high energy neutrinos in astrophysical sources because protons from cosmic rays can collide with photons inside astrophysical sources. So there is a huge uncertainty and we don't know practically anything about what to expect. We hopefully will know by the end of 2040 or so. But here I would like to focus, on a somewhat different physical question that we can ask by looking at these data. So the main feature that I would like to emphasize is that these neutrinos are the highest energy neutrinos that we will ever observe, if we will observe them. So since they are so energetic, they are sensitive to fundamental interactions at an energy scale that cannot be probed by any kind of experiment we have on Earth. So this makes them an ideal probe of particle physics at high energy scales. So the question I would like to pose here is, what do these neutrinos tell us about particle physics interactions? And the answer, as is becoming apparent, is that they can tell us a lot. There are more and more papers coming out every day that try to find more elaborate ways to extract particle physics information from data from high energy and ultra high energy neutrinos. Here I will just catch a couple of representative examples. One is, for example, to try to investigate the properties of non-standard interactions of neutrinos. We are used to thinking of neutrinos producing an astrophysical source, reaching Earth, and in between they do nothing. They are pretty boring because they do not interact. But if they have interactions beyond the standard model at a very high energy scale, they could, for example, scatter off dark matter, which populates the extragalactic environment, or maybe they could scatter off the relic neutrinos from the cosmic plasma. So this is a kind of thing that is being analyzed. Another possibility is that neutrinos could oscillate in a non-standard way. Again, we are used to thinking that neutrinos oscillate just because of the difference in masses between different mass eigenstates, but that's not the only possibility. In fact, originally the solar neutrino problem, people were trying to solve it by trying to violate some fundamental symmetries like Lorentz invariance or equivalence principle, because when you do that, you also introduce some additional sources of neutrino oscillations. But what I would like to focus today is, in a sense, somewhat more radical, in the sense that we could have neutrinos produced entirely in a non-standard way. So neutrinos entirely produced by processes beyond the standard model. And the example I will focus here is the case in which neutrinos are produced in the decay of very heavy dark matter particles. We already had a talk about this, I think, on Tuesday, but so maybe you're already familiar with the general idea, but I will go through it anyway, so we're all on the same page. So, and for this, of course, I need to introduce what dark matter is. I guess most of you know. So dark matter is just a component of the universe that behaves like matter, but is non-visible. So it doesn't emit electromagnetic light. And how do we know it's there? We know it's there because, as any other form of matter, it produces its own gravitational field. And we can measure gravitational field by measuring, for example, the speed of bodies subject to gravitational interaction, as is the case on rotational curves in galaxies, or maybe by measuring the effect of gravity on the distortion of light, as it happens with gravitational lensing. In all these cases, we can measure the gravitational field, and we can compare it with the gravitational field that we expect from visible matter. And whenever there is a mismatch, we can claim that there is evidence for something non-visible. And we know that there is a mismatch from galactic scales, so kiloparsec scales, up to the cosmological scales, because we have seen this mismatch also in the cosmic microwave background anisotropies. So even though it's not the only explanation, it's quite plausible that there is a form of dark matter, so a form of matter that is non-visible. And the simplest explanation for it is that this dark matter is composed of particles. That's what mostly resembles what we know about particle physics. So dark matter could be made up of particles, and simply that are non-electromagnetically interacting. And the paradigm, the original paradigm was that dark matter could be made of weakly interacting massive particles, WIMP for short. which is a kind of massive neutrino. So it's a particle which interacts with cross sections smaller than the weak cross sections, and with a mass which was typically assumed to be in the range of in the ballpark of the GeV to tens of GeV, never larger than, I think, 100 GeV. So a number of experiments have looked for this weakly interacting massive particle, but up until now, there have been only null or controversial results. This is a collection of, from 2018, a collection of constraints on the cross section for between this weakly interacting massive particle and nucleons. And the fact that there are early constraints is pretty self-explanatory. There is no evidence for dark matter up until now in this mass range. And this motivates a kind of extended search for dark matter candidates that are either lighter than this mass range or heavier than this mass range. And here, for reasons that will become apparent in a moment, I will focus on the heavier mass range. So if dark matter is made up of particles that are particularly heavy, heavier than, for example, hundreds of TeV, then these particles, if they are coupled to the standard model, can decay into particles of the standard model. This is the framework or paradigm of indirect detection. We have dark matter on a galactic and extragalactic scale that decays into particles of the standard model. These particles reach the Earth, and we can try to detect it. The critical quantity here is the mass of these dark matter particles, because the mass of the dark matter particle sets the energy scale at which we expect these particles to arrive on Earth. In particular, if the mass of the dark matter particle is larger than 100 TeV up to 10 PeV, remember that WIMPs arrive up to 100 TeV, so this is just above the WIMP mass scale, then we can expect these particles to produce neutrinos, which can be detectable inside IceCube. But here I would like to focus on the even heavier case. So if dark matter particles are made of particles which are more massive than electron volt, up to even zip electron volt, they could produce neutrinos which are in ultra high energy range, which will be explorable by these ultra high energy neutrino telescopes that I mentioned a moment ago. So here I would like also to tell something else, which is that in the decay of these dark matter particles, we do not expect just production of neutrinos. We expect production of any stable particle coupled to the standard model. So we also expect production of gamma rays and of protons and electrons. And in principle, the combined signature of all these particles gives us powerful information, much more powerful than using neutrinos alone. Here I will just focus on neutrinos because we are a neutrino school, but I think it's very important that we have a multi-messenger view of this phenomenon. So how do we analyze the physical setting? How do we describe the physical problem? I would say the description of the problem factorizes pretty neatly into 3 steps. First of all, we want, and this is also kind of pipeline of how we analyze beyond standard model effects on astrophysical neutrinos in general. First of all, we want to understand the particle physics. In this case, we want to understand how an individual dark matter particle decay and what is the spectrum of the neutrinos that are produced in an individual decay. Then we want to understand the astrophysics. We want to understand in what astrophysical places these neutrinos are produced and how do they propagate in the astrophysical environment up to the Earth. And then finally, the question that is probably most interesting from the phenomenological point of view. Can we detect this effect? Can we detect these neutrinos inside our detector? And I will start obviously with the first question. So how many neutrinos can we expect in a decay of an individual dark matter particle? And to do this, first of all, let's introduce the main characters, so the main parameters that we need to describe the physics of dark matter. Essentially, there are 3. First of all, we need to know the mass of the individual dark matter particle. I have already mentioned it. The mass of the dark matter particle essentially sets the energy scale at which we expect these particles to arrive at Earth. There is a second parameter, which is the lifetime of the individual dark matter particle. The lifetime measures how fast these dark matter particles are decaying. The shorter the lifetime, the faster the particles are decaying, the more neutrinos we can expect at Earth. So essentially, this lifetime is a normalization parameter for us because it tells us how many neutrinos can we expect to see at Earth. And then finally, of course, we want to know about the particle physics model. We want to know about the coupling, the Lagrangian coupling of the dark matter particle with the standard model particles. And what is traditionally done to simplify things is to just assume that the dark matter particle is coupled to pairs of fermions in the standard model. This is just a choice. One could make more complicated choices. It's not hard to analyze more complicated choices, but I will stick to this, which is particularly simple. So we'll just assume different models of dark matter particle coupled to pairs of fermions. Okay. So what is the spectrum of the neutrinos that we expect to be produced in the decay of the individual dark matter particle? In a very naive fashion, we could think that if dark matter decays into pairs of neutrinos, then it will produce 2 neutrinos Each one has an energy which is half the mass of the dark matter, and that is the end of the story. And if dark matter decays into any other kind of fermions, it produces no neutrinos. This is a very naive scenario, and it's wrong because it's so naive. The reason it gets wrong is that the final state particle at this very large energy, which are larger than 100 TeV, can emit W bosons. W bosons, recall, have a mass of 80 GeV, so they are particularly light, even though not for us, but they are particularly light at this energy scale. So they can be emitted pretty easily from a kinematical point of view. So one again could make a naive comment and say, okay, but these processes must be suppressed because each time I emit a W boson at the Feynman diagram level, I have to introduce a coupling constant. And so the probability of this emission should be suppressed by factors of the fine structure constant for the weak interaction, which is of order of 0.01. So we could say, okay, this is suppressed by a factor of 1%, but this is again wrong. The reason it's wrong is that the W boson is a fairly soft particle at this energy scale. It's 80 GeV, so it's much softer compared to the energy scales we're thinking of. And we know from quantum electrodynamics that emitting soft particles is easy. In fact, it's even nearly compulsory because the probability of emitting soft particles is enhanced by factors of the logarithm of your energy scale versus the energy scale of the soft particle. In our case, the mass of the dark matter over the mass of the W boson. If this logarithm becomes sufficiently large, which happens for masses just larger than about some hundreds of TeV, this probability can become larger than 1. And if the probability becomes larger than 1, the real scenario is going to look more complicated because we imagine to produce a lot of these W bosons. And of course, it becomes difficult to treat. The way we treat this problem is by using the energy cascade paradigm. We have the initial energy of the dark matter particle, which cascades down into a huge numbers of final state particles. So it's treated just as in QCD, we treat hadronization. We solve the Antarelli-Parisi equation for the cascade of energy due to this emission. And this has finally been done only in 2020, so not very much ago, and with some limitations. But it's finally been done, and people have published the result in this HDM spectra code. So up now, if we want to do indirect detection at this very large energy scale, we just need to use the software which contains the spectra of the particles produced in the dark matter decay. So the second question now is the astrophysics. Where do we expect these particles to be produced and how do they propagate to the Earth? We expect these particles to be produced in a decay of dark matter in two main environments, our galaxy and outside of our galaxy. In our galaxy, we know that our galaxy is populated by dark matter particles, which are distributed as in a halo, so a kind of cylinder which surrounds the galactic disk. The thickness is about, I think, hundreds of parsecs as an order of magnitude. And so clearly the signal is expected to be anisotropic, because if we look at the galactic center, there will be a lot of dark matter particles decaying, rather than if we look in the anti-galactic center, which is in the opposite direction. So if we want the diffuse neutrino flux from this component, we just need to multiply together the inverse lifetime, which tells us how many particles are decaying per unit time, the spectrum of neutrinos produced in the individual dark matter decay. I have just explained how we get it. And of course, we have to take into account the fact that neutrinos mix because they propagate incoherently as mass eigenstates. So there is a probability conversion from flavor alpha to flavor beta. And then finally, we sum over all dark matter particles inside the galaxy, which means integrating over the density profile of the galactic dark matter. So in addition to the galactic production, there is also an extragalactic production because dark matter is also present on a cosmological scale. We expect this extragalactic production to be mostly isotropic because of the cosmological principle that tells us that it's distributed homogeneously. And I think the most important feature about this extragalactic production, I will go fast on this, is that the spectrum needs to be redshifted. So that means that the neutrinos will arrive at the Earth with lower energy compared to the galactic one. So we expect them to dominate at lower energies. Okay, so we finally get to the interesting question, which is, can we detect the neutrinos coming from dark matter decay? Here we have a big problem. That is that we don't have the experiments yet, and we don't know the astrophysical fluxes. So it's full of unknowns. And a simple way to make this comparison is to simply take the sensitivities of the experiment, which I recall you is just the minimum flux that can be detected on a very rough level, and compare it with the dark matter fluxes that are shown here. So these are dark matter fluxes for 3 different decay channels. This is chi, which goes to BB bar or tau tau bar or nu nu bar. For different choices of benchmark parameters. And we could just say, if the flux is above the sensitivity, then it should produce neutrinos visible inside our detector. This is a simple way of doing things. Here I am showing sensitivities for the 4 neutrino experiments that I mentioned in the beginning of the talk. Just recall it's ground at an OG, and then there is the radio array at IceCube Gen 2. So the conclusion that we can draw from this figure is that if the flux is larger than the sensitivity, we could detect in the future. And if by 2040 we have detected no neutrino at all, yeah, so that means that the neutrino fluxes from dark matter decay cannot be too large, because otherwise it would have produced some events in our detector and we would have seen it. So we can draw constraints by requiring that the probability of observing no event is larger than a threshold value, for example, the 95% confidence level, which is typically used. So we did this and we obtained these constraints in the plane of the mass of the dark matter versus the lifetime of the dark matter. So the lifetime of the dark matter cannot be too short in this case, because otherwise it will produce too many neutrinos and we would see something. But this, so just for comparison, this gray line here are the actual constraints, the constraints that are already present from, I think, IceCube, Pierre Roger, and Anita. But this is only if by 2040 no event will be detected, which is not an optimal scenario because we hope to detect something, of course. So where is the catch? The catch is that we also expect it to be astrophysical neutrinos, neutrinos produced in standard astrophysical or cosmogenic origin. So here I am showing just 2 benchmark fluxes. The red curve is one benchmark cosmogenic neutrino model, and the blue one is a model of neutrinos produced by cosmic rays around pulsars. We chose this one just because it's a model that predicts a lot of neutrinos compared to other astrophysical models. If there are neutrinos that produced in astrophysical sources, they could be detected inside our detector. And there is no way we can tell on a one-to-one event basis whether that neutrino come from dark matter decay or whether that neutrino come from astrophysical sources. So in a sense, the astrophysical neutrinos, which is a signal that we would like to detect, for this particular analysis is a background, because we don't know how to distinguish them. That means that if one of these models is correct, let's say, for example, the cosmogenic model, then by 2040, we will have detected some events, and the constraint that we can draw on dark matter decay will necessarily be weaker, because we have detected some events that we cannot say whether they come from dark matter decay or not. So how do we deal with this, since we do not have the data yet? The way we deal with this is to simulate. So we assume that one of these models is correct, for example, the cosmogenic model. We simulate the response of the detector to this cosmogenic model, assuming that there is no dark matter. We simulate the data samples that will come out of this flux, and then we obtain the constraints by comparing the dark matter model with the data that we will have detected. And so what we get is the constraints that you find here. So the blue ones are just the ones that I was showing earlier, but the red ones and the cyan ones here are the constraints that will be, yeah.
You showed previously that the prediction for cosmogenic neutrino flux are so huge, so it's like 2-3 order of magnitude. How you can deal with that in this case?
Yeah, so this is the, let me go back. So this cosmogenic one is just one prediction. So remember that if the cosmogenic flux is particularly low, it will produce no event. Okay. So we go back to, I can't, yeah, we go back to this blue curve here if the cosmogenic flux is particularly low. So this is this red curve, I think it corresponds to one of the higher cosmogenic models that we found at the time. Maybe now there are more, but at the time it was one of the highest. So if you have only cosmogenic models, then you can expect your constraints to be anywhere in between this region here. Yeah. So of course, even for a fixed model of cosmogenic or astrophysical, you still have a band of expected constraint, because even if you know how many events you expect in your detector, there are Poisson fluctuations. So there will the number of observed events will always be different than the expected number. But this is the final result. So these are the constraints. In particular, the blue one are the expected constraint in the case that we have a huge astrophysical background coming, in particular case, from pulsar acceleration. So what I think, so of course the constraints are weaker than if we didn't have any astrophysical background, but still what I think is interesting is that even in this case, the constraints are more than one order of magnitude stronger than the actual constraint, which tells us that the ultra high energy neutrino detectors are definitely going to advance our understanding of these very heavy dark matter properties. And so I can finally go to my conclusions. I would say in one line, the main conclusion is that astrophysical neutrinos, which of course were born to try to answer astrophysical questions, are also an ideal probe to try to understand better particle physics interactions. I try to illustrate this with one specific example, which is the case of decaying dark matter. Right now, IceCube is already the most competitive probe of dark matter decaying into neutrinos alone. But in the near future, we will probably be able to probe heavier dark matter by using these ultra high energy neutrino detectors that are under construction. And let me conclude with one final comment. I didn't have much time to spend on this, but it's very important. Neutrinos are really just one side of the game, because in the decay of dark matter, as well as in many other extensions of the standard model, we expect correlated signal in neutrinos and in gamma rays. And the combined information of the two is definitely what is going to provide the most powerful information out of this. And with this, I conclude. So thank you very much for your attention.
Thank you, Damiano. Yeah, I was also wondering how much you can actually learn from the gamma rays that you produce there.
Yeah, so that's, we did it only for, where is it? So these are constraints from actual gamma ray measurements. So this, the black, I was confused. So the black curves here, the black curve here is the constraint that we get from the present gamma ray measurement. And I think for the dark matter to nu bar channel, Jali showed a very nice compilation of constraints for many different experiments other than just these ones. But yeah, this would be the scenario. So you see that the constraints that I just showed, the one that you can get from ultra high energy neutrinos, are this red and blue line. In some regions, they are still stronger than the gamma ray constraints because your decay channel is preferentially producing neutrinos compared to gamma rays.
There are also some photon fraction limits from Auger that you could maybe use here.
Right? Yes.
Because you had these extremely, yeah. So
yeah, I think Auger is included here. It's this purple line here, and also the blue one.
Do we have other questions? Yeah.
Thanks for the call. I was wondering about this HDM spectra code you were talking about. Does it assume the same production of standard model particles from dark matter decay that you do, or is it like a variable that you can change?
You can change it. So the HDM spectra has a collection of primary dark matter to decay channel. But let me also mention that if you have, okay, so HDM spectra, as I also did here, assumes decay into pairs of fermions.
Okay.
But it's fairly easy to combine the things because the showering is the complicated part, the showering that I showed. Right. And the showering happens only after the dark matter has decayed. So if you have, for example, I don't know, dark matter to tau plus B, you can just mix up the two things. You take the tau bar channel, the BB bar channel, you take the average and you get, yeah, you can get information on, I think, on any kind of decay channel by using HDM spectra.
Okay. And then for the assumptions you made, is it just because they were the simplest, or do you have more physical motivation for it?
For the decaying to pairs of fermions?
Right.
No, I don't think there is any physical motivation. I don't think there is any model builder that would really think of this as natural. Yeah. It's just that it's fairly easy to compare with the literature because people have historically always done that way. So it's fairly easy to compare with the literature.
Okay.
And again, if you want different decay channels, you can just mix up things. And,
right.
Do you have any other question? Yeah.
Great talk, by the way. So do you consider in your work any like C/B interactions with your dark matter decay products? Because at this point, you should be able to see a resonance with that, and that would actually lower your flux. So do you consider those?
Okay, so when you talk about C/B, you're talking about standard, like a weak interaction between neutrinos.
So C/B interacting with your high energy neutrino here. Okay. You should be able to see a resonance.
So if it's the standard model, like weak interaction, I think it would be at energies too high compared with the sensitivities of the experiment, because it would be like, how we were saying, like 10 to the 21 electron volt. So compared with the sensitivities of the experiments, where is it here? Yeah, 10 to the 21 electron volts. So it's 10 to the 30. Yeah, 10 to the, no, it's not 10 to the 30. It's 10 to the 12 GeV. And 10 to the 12 GeV is more or less here. So even though you have a spectrum here, the sensitivities of the experiment are too low. You cannot detect it. If there are non-standard interactions, then you can have non-standard interactions with the C/B, and then the mass of the mediator you can tune. So you can move the resonance around, and you can also have it in the range of, for example, ground. In the case of dark matter decay, like this interaction of non-standard stuff, people don't typically do it, but the non-standard interaction, people have done it. We also worked on it, like in the ground region, you can see distortions of astrophysical spectrum in the ground region because of this interaction, non-standard interaction with the relic neutrinos. I don't know if that answers.
Just one comment about what you just said. I think it would be interesting. So you have 10 to the 12 GeV neutrinos, right? Those interact with the C nu B.
They are cascaded.
They're
down.
cascading down.
Yeah, it's a
So
possibility.
you could get a bump at some lower energy
lower
because
energy,
of the
yeah.
cascade of the Z.
I agree, it's a nice thing.
Thanks for the talk. Do you know what dark matter mass range IceCube upgrade would be looking at? Like
Can you repeat, please?
the dark matter mass range that IceCube upgrade would be looking at?
Yes, so the, let me go. You mean IceCube, right? So this is a bit outdated. The IceCube collaboration made their own constraints, I think, some months ago. So I don't have on the slides here. This is a work from 2019 that we did. And these are the constraints that we got from IceCube. So the mass range is more or less from 100 TeV to 10 PeV. And then they start to go up, depending on the channel. It also depends on the channel because, for example, for BB bar channel, the constraints raise much faster. So they become weaker much faster with the mass range increasing because you produce neutrinos only by the cascade. So if you have a very large mass, you pile them up only at very low energies, and that's why it increases so fast in this case. But the mass is more or less this one. The ballpark is up to 10 PeV.
Thanks.
Any final question for Damiano? See any hands, so let's thank Damiano again.
Thank you.